All right. So, so good. All right. So thanks for coming back from lunch. First talk of the afternoon, right, is always
You're,
challenging.
you're
But we have Danie here. We'll have us really right pay attention here. So, with Danie, please go on with the introduction to Steinberg algebras.
okay. Um, so yesterday we spoke about groupoids. In particular, we talked about topological groupoids. We gave a couple of examples, which included groups, it included equivalence relations, it included dynamical systems, and also directed graphs. So today we want to look at how we can build algebras from those groupoids. So maybe just a quick recap. A groupoid, we said, is some set with an operation called multiplication defined on it. But multiplication might not be defined for all elements, right? So we had this notion of a composable pair, meaning that we can multiply gamma and eta, and that's only possible if the source of gamma is equal to the range of eta. So in particular, a nice way to visualize those is with little arrows. Then we have the source of gamma there and the range of gamma there. So to be able to compose, well, I guess I've got the picture up here as well. We needed inverses as well. There's the picture. To be able to compose eta and gamma in that order, we need the range of gamma to be equal to the source of eta. And of course, we also need the idea of an inverse. So if this is gamma, then the inverse of gamma would be the same arrow, just in the opposite direction. So here we would have the source of gamma inverse and, oh, sorry, I beg your pardon, the range of gamma inverse, and that would equal the source of gamma. So this is actually an important property, right? And the same for the source of gamma inverse, that's equal to the range of gamma. So that's fine. We then said that a groupoid is a topological groupoid if it has a locally compact topology in which multiplication and inverse operations are continuous. We then went into more specific cases. So one was an étale groupoid. For that, we need the idea of a bisection. So an open set in G is a bisection if we, whenever we restrict the range and the source maps to be, then they are homeomorphisms onto open subsets of the unit space. And if the groupoid has a basis of such open bisections, then the groupoid is étale. So that's one of the equivalent conditions for a groupoid to be étale. All right, so now, one step further. Instead of only considering open bisections, let's also require a basis of compact and open bisections. So in that case, we call the groupoid ample. And these are the groupoids that we want to work with when we construct Steinberg algebras from the groupoid. So for the remainder of today's talk, let's, whenever we're not dealing with a specific example, we'll assume that G is a Hausdorff ample groupoid. Okay. All right. Now, let's talk about the building blocks of Steinberg algebras, the algebras that we associate with ample groupoids. And I don't think there's any harm in assuming that we want to construct an algebra over a unital commutative ring, and we endow the ring with the discrete topology. So we say that a function from the groupoid into this ring is locally constant if every point in the groupoid has some neighborhood on which the function is a constant. Right? I think that is fairly intuitive. Now, since the ring has the discrete topology, it follows that f is locally constant if and only if it's continuous. So the forward direction holds for any topology on R, but the reverse direction holds because R has the discrete topology. So we can use locally constant and continuous interchangeably as long as we have the discrete topology on R. Okay, now, suppose we've got some locally constant function from the groupoid into this ring. Then we define the support of F as all the groupoid elements on which the function is non-zero. And the support is a Clopin set. Right, so you can try and check that, see if you can prove that. Okay, so these guys are going to be the building blocks of the Steinberg algebra if we also assume that the support is compact. So let's take ARG to be all functions from G to R such that the function is continuous with compact support, or such that the function is locally constant with compact support. So how do we turn this into an algebra? Well, addition is defined pointwise. That's fairly straightforward. Then this ARG becomes an R module. The next one is multiplication. So this is a complicated looking expression, right? But let's see if we can make sense of it. The first thing is products such as this are called convolution products. You may have seen them in Fourier analysis as well in terms of integrals. But because an ample groupoid is in particular an étale groupoid, the pre-image of any unit under the source map is a discrete set, and that allows us to work with sums as opposed to integrals. Okay, so what's happening there? Let's see. So F star G denotes some function obtained by multiplying F and G. So when we apply that to a gamma in G, then we look at the sum of all F of eta, G of eta minus 1 gamma, set over etas such that the range of eta is equal to gamma. So I suppose we need to make sure that this makes sense, right? So if the range of eta is equal to the range of gamma, then by this little explanation above, it means that the source of eta inverse must be equal to the range of gamma, right? And this implies in turn that the pair eta minus 1 and gamma is composable. So eta minus 1 gamma is perfectly fine. Right, so for example, those kinds of elements make sense. They are meaningful. So here's a little exercise that you can go and try. This sum must necessarily be finite. Otherwise, what does it mean? Right? The fact that it's finite follows because we are working with a ring with a discrete topology, and the functions are locally constant, and they have compact support. All right, so see if you can show that there is only a finite number of etas that we can apply this expression to. Right. Okay, so this is convolution product. This is fairly standard. And then with these operations, we obtain an R algebra, which is called the Steinberg algebra associated with the ample groupoid G. Okay. So just to reiterate, the Steinberg algebra is essentially just a bunch of functions from the groupoid into the ring, but such that they are continuous with compact support. Okay, is that fine? All right, so let's consider a specific case where the ring is equal to the complex numbers. So if we consider the complex numbers, then we also have an involution or complex conjugation, if you like, right? So the operation of taking a complex number Z to its complex conjugate for Z in C is an involution. And therefore, we can add another operation. So again, we start off with those functions from G into R. pointwise addition, scalar multiplication. So this time we don't have an R module, we have a vector space. We define multiplication. And then we can also define an involution on the algebra. We define f of any gamma star as the complex conjugate of f of gamma inverse. So in this instance, we end up with a star algebra. And it's worth noting that the fact that we used C is not really anything special. If you have a ring, a unital commutative ring with an involution on, similar to what Leah described this morning, then you can also define an involution and obtain a star algebra from that. Okay, so that's fine. We know that a Steinberg algebra consists of functions from the groupoid into the ring, but there's a nicer description than that. Before that, we need to discuss the set of all compact open bisections of G, right? So this is a basis for the topology on G. It turns out that this B co is actually an inverse semigroup, right? So that means we have a operation defined on a set that is associative, and there exists a unique inverse for every element. So if you have X in the semigroup, then there exists some unique Y such that X is equal to XYX and Y is equal to YXY. This may look familiar from some of the stuff that Leah did this morning as well, right? So in other words, this collection of compact open bisections actually forms an inverse semigroup. The set of idempotents is exactly the compact open bisections contained in the unit space. Right, so what can we do with this? First, we observe something. So let's denote 1u by the characteristic function on the compact open set. In other words, if gamma is in U, it gives us back 1, where 1 should be interpreted as the unit of the ring, or 1 in the complex numbers, depending on what your ring is, and 0 otherwise, right? So then clearly 1u is locally constant. It has compact support. It lives on U, which by definition is a compact open bisection, which means that all of these 1u's, all characteristic functions for U contained in that set, is also a function in the Steinberg algebra. We can say even more. It turns out that these functions generate the whole Steinberg algebra. So this is especially handy to work with, right? It's much easier to work with characteristic functions than just some arbitrary function that is constant or locally constant with compact support. So this proposition, I believe, was first proved by Clark, Sims, Farthing, and Tomford. So for a moment, ignore this part. I should have put a pause in there, but looks like the pause disappeared somehow. Let's just focus on that, right? So if you take the R span of all of the characteristic functions that live on compact open bisections, then that generates the whole Steinberg algebra. So let's explore what the operations in the Steinberg algebra look like when we apply them specifically to these functions, right? Because these are, in a sense, the elementary building blocks of the Steinberg algebra. So it would be informative to know what, for example, multiplication looks like and what inverses look like, or convolution rather. So suppose we've got a U and a V. Then we claim that the convolution product is equal to the characteristic function on UV, where this UV is multiplication in the inverse semigroup, right? So in other words, multiplication in the Steinberg algebra corresponds to multiplication in the inverse semigroup. Okay, so to see this, let's write out the formula. So this is just how convolution is defined, right? And since that is a characteristic function, the 1 subscript u and the 1 subscript v, it means that this expression will be 1 if we know that eta is in u and eta inverse gamma is in v, and 0 else otherwise. All right, so what does it mean over here? Let's see. Well, if eta is in u and eta inverse gamma is in v, then those two elements should be composable, because we know any groupoid element and its inverse is composable, and then we have associativity, right? So that implies that we can compose them, and what we end up with is just gamma. So gamma must be an element of this product in the inverse semigroup. All right, now, what about the other way around? Suppose we start off with something in this product, some gamma. I beg your pardon. Then gamma must be equal to eta alpha, where eta is in u and alpha is in v, right? So let's take this eta and multiply with the inverse of eta on both sides, so that we can get alpha alone on the right-hand side. All right, so that's this expression. So analyzing this, we see that the source of alpha must be equal to the source of this expression, which is the source of eta inverse. But that means the source of alpha must be equal to the range of eta, and that must be equal to the range of gamma, right? So this is exactly the expression that we have in this sum. In other words, for this particular gamma that we started off with, this expression is 1. Which shows us that this kind of product amounts to exactly the characteristic function on the product in the inverse semigroup sense. All right. Is that okay? So the idea that you have this inverse, in fact, that was how Ben Steinberg originally developed Steinberg algebras. He studied algebras associated with inverse semigroups. And then the connection was made with groupoids. So the operations on the inverse semigroup on the compact opens is mirrored in the Steinberg algebras operations. Okay, so we've dealt with that. And then if you have a ring with involution or the complex numbers, then the involution of that function is just one of the inverse of the compact open in the inverse semigroup sense. Okay, so that's pretty cool. Inversions in the Steinberg algebra correspond to inversion in the inverse semigroup. Right, so we have some more properties that we can highlight here. Oh, all right, so in this instance, we're considering two compact open sets, but this is restricted to the unit space. So imagine we've got two compact open sets contained in the unit space, not in the groupoid in general, just in the unit space. Then it turns out that multiplication, convolution, amounts to pointwise multiplication of characteristic functions. Okay, so to see this, suppose we've got two compact open sets contained in the unit space. Then multiplication is defined in the semigroup sense as just the product of all elements in U with all elements in V, but when it makes sense, right? When it's meaningful. And because U and V are now both units, it means that the range of U is equal to the source of U, which is equal to the range of V, which is equal to the source of V. In particular, this means that U and V must both be in U and in V. So the lowercase u and lowercase v must be in big U and big V. So in particular, it must be in the intersection. And from that, we see that the convolution product is equal to 1, the convolution product of the characteristic function on U with the characteristic function on V is the characteristic on UV in the inverse semigroup, but that's just equal to the intersection, which is the same as the usual pointwise multiplication of characteristic functions. Okay. And this example illustrates it for characteristic functions, but you can apply the same kinds of arguments to any function that lives on the unit space. So if the support of a function is contained in the unit space, then convolution products correspond or are equal to pointwise products. Okay. Right, is this okay? Any questions, any comments? All right. So the moral is we've got some semi-group that we associate with the groupoid in terms of the compact open bisections. And those operations correspond to multiplication and inverses, or I beg your pardon, involution in the Steinberg algebra. So when will the Steinberg algebra be unital? Well, only in the case that the unit space is compact. And if the unit space is compact, then the unit of the algebra is just the characteristic function on the unit space. Okay. You can do some small calculations yourself to go and check that out. And another interesting property is that if you consider the unit space as a groupoid itself, then the Steinberg algebra on the unit space is contained as a subalgebra in the Steinberg algebra of the whole groupoid G. It's worth mentioning that this property does not hold in all cases of algebras associated with groupoids. For example, if you work with groupoid C star algebras and your groupoid is not étale, then this is not guaranteed. Okay, so this is indeed a special property. Okay. How about examples? Do you remember the matrix groupoid that we looked at yesterday? So maybe we can do a brief recap, if you like. Is it necessary? Would it be helpful? Okay, all right, so let's do that then. So we said that we consider n natural numbers, Cartesian product with the same set, and then we had that I, J, and KL is a composable pair if and only if J is equal to K, right? And in this case, we then had multiplication defined as, so the middle two terms collapse away and we just keep the two outsides, right? And then we also had that inverses essentially just reverses the order. And with these operations, we obtain a groupoid. And this is actually just a special kind of groupoid, a special kind of equivalence relation. Okay. So if we want to construct a Steinberg algebra from this groupoid, so the first thing we need to sort of get a handle on would be compact open sets. Any idea what those would be? I suppose just about anything, right? Because this is the discrete topology. So anything finite would be compact and open. And since we're working on a finite set, just about anything. But in particular, for every I and j between 1 and n, that should be a compact open set. Correct? So we can likely generate the Steinberg algebra with characteristic functions of this form. Yes? Where we range I and j between 1 and n. So let's see how this would work. That's the span of all of those elements. And for simplicity, let's take the complex numbers as our coefficients. Right, so suppose we've got two elements of this kind. So in this instance, that's a j. I don't know if you can see that. Does it look like an I or a j? It looks like an I to me. It should be a J, please. All right, change that to a J. So we've got essentially two elements of the Steinberg algebra here, where each one of those represent a compact open bisection. Right, then convolution, we know, gives us the characteristic function where this product is now in the inverse semi-group sense. But because each of those sets only have one element in them, it's just the multiplication of those two elements. Now, we can only multiply those two elements when J is equal to K, right? So that means that the right-hand side will be equal to delta JK times 1 IL. Right, where that's sort of the Kronecker delta. If J is equal to K, it is 1, 0 otherwise. And what does this tell us? Well, this tells us that these are actually matrix units. So in particular, or as an example, this element can be represented as the matrix that has a 1 in the second row and third column and zeros elsewhere. Because when I multiply these matrices, they follow the same algebraic structure as multiplying those elements over there. In other words, one can show that the Steinberg algebra associated with this matrix groupoid amounts to just getting all the n by n matrices with complex entries in them. Okay, so this is a very, very concrete example of a Steinberg algebra. Is that okay? Right. So the following example is a little bit less concrete, but nonetheless, let's see if we can go through the motions. It'll work more or less the same. So in this instance, suppose we've got a discrete group and it acts on a locally compact Hausdorff space by homeomorphisms. And also we need to assume X has a basis of compact open sets. Let's call that B, right? And that way, the transformation groupoid will be an ample groupoid. So the first thing we want to do is, and that's the point of this example is, there's a sort of a usual way to construct an algebra from a dynamical system. And it turns out that that algebra that you construct is isomorphic to the Steinberg algebra of the groupoid associated with the action. So I won't give the explicit isomorphism, but I'll go through the construction of the skew-group ring, and then just give the description of the Steinberg algebra and state it as a theorem. You can try and work out the details yourselves. That will be a nice exercise. Okay, so suppose we've got some function from the group into the set of homeomorphisms that preserves the group operations. So this is what we mean by an action, right? So each phi h is a homeomorphism on X. So the skew-group ring associated with the dynamical system Hx is a non-commutative ring that captures the dynamics. So one way to construct it or to view it is to consider all locally constant functions on the space X. And we would like them to have compact support as well. I don't think I put it in there. So then this becomes an R algebra with pointwise operations. Pointwise addition, pointwise multiplication. So we get this algebra. So now this action induces an action of H on this R algebra, LC of H, in the following way. We define a map from H into the automorphisms of LC of X by declaring that phi hat of H of F applied to some X is just the composition of F with the homeomorphism phi H. Okay, in this way, we get an automorphism. Then this gives us an action of H on the R algebra. All right, so started with the dynamical system, H acting on some topological space, and from that, we got a new action of H on an R algebra. The next step is to consider all formal sums of this kind. So this is the skew-group ring. It's all formal sums of this kind where AH is just some element of the ring, and delta H doesn't have a lot of meaning in itself. It's merely a placeholder. There's another view where you can view it as functions from the group into the ring, but let's just suppose the delta H plays the role of a placeholder indicated by the index of the group. These are coefficients, and we require that at most finitely many of these guys are non-zero, right? We don't want to deal with infinite sums. So the way we turn this into an R algebra is by defining addition. For the next example, I'll give the explicit mappings on the generators. Okay, so another example that we considered is that of a directed graph. I don't know if you guys remember this. Do you remember what the boundary path space was? So maybe let's write that down as a reminder. Right, so the boundary path space consisted of all infinite paths. We even looked at some particular examples. The union of all sinks and the union of all infinite emitters. So for example, just an infinite path. Something wrong? All good? Okay. Something like this that just ends in a sink. This vertex doesn't have any emitters. And finally, one that has an infinite number of emitters. So all these kinds of paths are boundary paths. And then we gave the boundary path space a topology in terms of cylinder sets, right? So before we get there, sorry. The groupoid is defined then as all triples where the first and third coordinates are of the form alpha x by beta x contained in the boundary path space, such that x is also in the boundary path space. Alpha and beta are two finite paths, and alpha and beta are used to determine the integer in the second coordinate by just taking the difference of the length of alpha by the difference of beta. Okay. So recall that G is an ample groupoid if we define ample groupoid where the compact open sets are given by the Z mu V. So maybe let's elaborate a little bit on this. So remember that if mu is a finite path, then the cylinder set at mu is the set of all boundary paths that start with mu, right? So take the path mu, and then all other paths that continue from mu that form a boundary path is in this cylinder set. And we could also form the punctured cylinder set if we have a finite set contained in the set of all edges leaving the range of mu. This is finite. Then we could consider the punctured is it the cylinders of mu e. Right, so we just exclude all the edges that are in that set F. And those sets form a basis of compact open sets for the boundary path space. So we could use them to define compact open basis for the topology on the groupoid, the graph groupoid. Okay. Is that fine? So in particular, now that we know what the basis looks like, it means that we can give a description of the Steinberg algebra. So the Steinberg algebra is, in fact, the span. That's a typo, right? It should be the span of all of the characteristic functions on compact open bisections. The fact that it's a bisection takes a little bit of work. So that's fine. That's okay. One can do calculations with that. So there's a little theorem that says that the Leavitt path algebra, it's not a little theorem, it's a theorem. It says that the Leavitt path algebra of a graph is isomorphic to the Steinberg algebra. I forget, did Leah introduce this Leavitt path algebra yet? She spoke about it, right? So you've got a graph, and then you look at the algebra generated by projections indexed by vertices and SE star, where E is an edge, subject to some conditions, and she went into detail about why we have to impose these conditions to get some smaller algebra that we can work with, right? So once again, the Leavitt path algebra is an algebra constructed from something that is very combinatorial in nature. It's a graph. And we can show that the Steinberg algebra on the graph groupoid is isomorphic to the Leavitt path algebra. And this is what the isomorphism looks like on the generators. So if you take any vertex in the graph, then it sends the projection indexed by this vertex v to the characteristic function on the ZVV. Right? So let me go back one slide. Consider this set, but instead of a mu and a nu, you have a vertex, v. So we're looking at all boundary paths that have source v and source v, and in the middle we just have 0, right? And then if you have an edge, and it takes s indexed by this edge to the characteristic function on ZE, comma, source of E. And again, for an edge, the ghost edge, S indexed by the ghost edge, takes it to 1Z. In this instance, we reverse the order of those two. We have source of E first, and then E. And this is the isomorphism on the generators of the Leavitt path algebra, which one then can extend to linear combinations, etc. Typically, to prove these kinds of isomorphisms, one uses so-called uniqueness theorems. One can prove that they are surjective. For example, in this instance, to see that it's surjective, a typical generator in the Steinberg algebra has that form, Z mu F nu, and you can go and see that, or you can try to see that that can be expressed in this way, which is exactly formed by elements of that type. So this is just a linear combination of elements of that kind. Therefore, this map is in fact a surjection. To show that it's injective, often uniqueness theorems are used. I don't think that I would have had time today to go into too much detail about uniqueness theorems, but they do play an important role in the theory. And essentially what a uniqueness theorem says is, if you have some homomorphism from one algebra onto another algebra, then it's sufficient to check in the injectivity on some sub-algebra of the one algebra. So you have, suppose, a function from algebra 1 into algebra B, and if there's a specific kind of algebra, let's call it C contained in A, then it's sufficient to check that this is injective. And those kinds of theorems are referred to as uniqueness theorems. Okay, so I think I will stop there for today. Any questions or comments on this? Yes. Go for it. Oh, do you want a mic?
Hello. Okay. Thank you for the awesome talk. It's very interesting, most especially that I'm working with Leavitt path algebras right now. So in this algebra, we are actually very curious and interested with weighted ideals in the Leavitt path algebra, and it is known to be generated by some subsets of the vertices. So I'm wondering, because of this isomorphism, can we also say the same thing with maybe some subgroupoid, if that's a term, I don't know, of the groupoid that we get, and also generate the same graded ideal as well?
Okay, so let me just make sure I understand the question. You've got a Leavitt path algebra,
Yes.
And
And you have the graded ideals in it, and it is generated by some subsets of vertices, essentially.
right.
And then, since we say that for some, let's say subgroupoids, but I don't know if it's that a if that's a term
Hmm.
of this groupoid, can we find something that relates these two stuff?
So the isomorphism that you get is a graded isomorphism, which I think will be helpful to start off with. As far as whether it sort of preserves the graded ideal structure, I don't have an answer for you on that. I know that I think Lisa Clark, who else? I forget.
Leah.
She had some co-authors, but they did some work on the graded ideals. So you can try and check that out. So to talk about the graded structure of Steinberg algebra, you of course need to have some co-cycle attached to it, and then that gives you your grading. But I don't remember any of the details of that paper. I didn't read it in detail. I'd be happy to look afterwards and see if I can find it. Okay.
Thank you. Thank you.
Okay.
Ask Ben, right? We can also ask
Oh,
Ben.
right. Yeah, of course.
Tomorrow, I think. Yeah.
Yeah, so I think the creator of Steinberg algebras, Ben Steinberg, he's speaking tomorrow afternoon as well. So that's an ideal person to ask about this too. Yeah. Yeah.
So when you were denoting here the trace function of 1z v, there is a 0 there that you're meeting, and the e source of v, there is a 1 there.
So sorry.
So just notation. Oh, just where it is there. The trace function. Don't we? Oh,
Oh,
you
so
just
sorry.
had
The previous slide.
Okay, go the previous one. Yeah. Okay.
Yeah.
Oh, that's perfect. Okay, perfect. The length. Oh, that's there. All right, perfect.
Right. So v is length 0, so you end up with 0 in the second
All
column.
right, and then 1 because it's already there, right? You don't keep the tree in the. You don't keep the cocycle. You just need the,
Yes.
use the path for the ones. All right. Okay. Questions? More questions? Anyone? Okay.
Okay.
Not. Let's thank Danie.
Thanks. Okay.
So next talk is in 30 minutes.